relevant to the example we'll do. So if we wanted to find the inductance per unit length for a solenoid of cross-sectional area A, what would we do? So inductance per unit length would be L over the length of the solenoid. So L over the length, our L equation is N times the flux over current, and then the length in the denominator adds to this denominator as well. And then last week we said that the total number of turns N could be replaced with the turns per unit length times the length. Okay, so I'm going to replace big N with little n times L, and that way I can cancel my L's on the top and the bottom. And then our flux, we said, usually reduces down to B times A, so we'll substitute that in as well. So now we have turns per unit length times the magnetic field times the cross-sectional area over the current. And then for a solenoid, this is the B field of a solenoid. B was equal to mu naught I times little n. So I can put that back in. Mu naught I little n times A over I. That allows me to cancel the current from the equation. And so then I can combine my little n terms, and I have mu naught n squared A. So let's think about this. If we're looking for inductance per unit length, all it depends on is the number of turns per unit length and the cross-sectional area. So the current running through your inductor falls out of the equation. And then my little comment over there, if you double the number of turns, because that's a squared term, you quadruple the inductance. So let's try example 30.3 and see, we'll see what that's all about. 30.3 says, determine the self-inductance of a toroidal solenoid with cross-sectional area A and mean radius R, closely wound with N turns of wire on a non-magnetic core. So, figure 30.8, you'll have to flip over the solution to see. I didn't copy the figure over, unfortunately. So, assume that B is uniform across the cross-section, that is, neglect the variations of B with distance from the center of the toroid. That allows us to keep this term B times A without having to do any integral stuff. So we're looking for the inductance, okay? We can summarize what we're given. Oh, that's one more. Okay. So they don't give us any numbers, but the things that we assume we would know the numbers for are things that they mention the variable for. So things we know, there's cross-sectional area A, mean radius R, N total turns, and there's a B field across the cross-section.
Camera.
Awesome.
So the camera needs to be plugged in because the battery doesn't have enough charge right now.
Okay.
So
Thank you, Liz.
I mean, there's anything else you need.
Over I. And then we can substitute for the flux. They said that the B field is, we can assume that it's constant across the cross-sectional area. So from the picture, this is a toroid. It's got loops of wire going around this donut shape.
It is National Donut Day, or was this week too.
Is it today? Actually, it was today. I thought about it last night that I was like, oh, I should buy donuts for you guys.
Supposedly,
Krispy Kreme.
Donuts down the hall.
Krispy Kreme is actually offering 1 free donut per customer today.
They always give you free donuts, though.
I know.
Like when you go and get them, like
True,
they
I
don't
agree,
give you
but
free
you know, I'm
donut.
just telling you.
They just want people to.
That would be it. Yes.
But today,
Okay,
if you
so
buy
there's
one,
our
you get
picture of toroid. This is the cross-sectional area that they're talking
2 for
about,
1.
and then they're saying the mean radius would be like to the very middle of the B field that's created in here. That would be the radius R. So that's what the A term here means, is that cross-sectional area. What did we do next over there? Then we plugged in the B field of a toroid. So we have to go back to our notes and look up the B field of a toroid.
Oh boy.
Okay, and I don't know it off the top of my head. That was lecture 7? Was it last week?
It was no. It was
2 weeks ago.
2 weeks.
2 weeks ago, yeah, that's
Yeah.
It was a while ago.
I didn't think it was last week. What did we say?
It was in our homework too.
Toroid. Mu naught I n over 2 pi r.
Yeah.
Mu naught I n over 2 pi r. Let's verify that's the same r I drew in my picture. And it is. Okay. So putting that in, I have L equals NA over I. And then the B term is all that stuff that we just added. Mu naught I n over 2 pi r. I cancels. And we're left with mu naught n squared A over 2 pi r. Let's check. We were given A. If we had, these are all the things that we could have numbers for if they gave us a number problem. So we have A, we have R, we have N. B dropped out of the equation. Actually, we didn't even need to make that substitution. But anyway, we would assume that we know our constants. So is that as far as we need to take it? Let's see what the book says as far as the answer. They came up with mu naught n squared A over 2 pi r. Okay.
That's it.
That's it. That's it.
Well,
I know it's not really fun when you don't have numbers.
Yes.
So they did in the evaluate section, they put in numbers here. So they said, let's say that there are 200 turns, the area is 5 square centimeters, and R is 0.1 meters. Then, putting in those numbers, you'd get an inductance of 40 millihenries.
Millihenries.
I still don't have a context for what that means.
That's just the
You know, I
weirdest.
think until you actually like make an inductor and use it in the
Millihenries.
circuit, it's like
You got a million Henrys. Good thing you don't know anybody.
milli.
Milli.
Not-
Oh, all right.
not-
Well, whatever.
Not mega. Milli is
A little.
a million.
A little
million?
Henry.
No, 1,000.
A little
A
Henry.
milli would be 1,000
Henry
Henry.
Jr.
Yeah.
All right, so we will take a break so we can set up the video equipment. And thank you, Saban, for recording some of that lecture.
That was fun.
So,
So why can't I tell this? I don't understand.